everybody, and welcome to the third class in our hands-on optimization masterclass. I'm Cristina Radu, and here is Felipe Brandão from AMPL. We will continue talking today about solvers. So let's see what is the agenda. As I mentioned, the reason that we can teach this class is that the supply chain has a certain data structure. So all the solvers are built starting with this data structure. So we are going to understand a little bit about it, and then we are going to see what are the typical objectives, inputs, and outputs in a solver from a business perspective. So, and this will also help us when we need to design a solver, like what should we look at in order to have a good design. And then how do we build the variables, dimension, and constraints based on this data structure? Because it's always going to be the same type of variables, the same type of constraints. So yeah, as I said, because the data structure is kind of fixed, then the structure of the solver it's fixed. And then we will discuss, Felipe will show you a little bit about the AMPL. We are going to go to the app that you're going to use to model, and then talk about sets, parameters, and other things. Now let's start. As I said, we have a data structure in supply chain, and this data structure is given by the supply chain itself. Because what are the concepts in supply chain? We always have a product, we always have a location, we always have resources on which we produce the goods, customers, where we deliver the goods, and suppliers, which are entities that help us increase our production, or supplier of raw materials. So you can have, the supplier of the good, of the finished good, or the supplier of the raw material. And to exemplify this, we have the demand. It's described by product and customer in one scenario, which is network optimization. In the other scenario, which is production optimization, the demand will be on the product location. This is here, I'm just giving a few examples. When it comes to production and also the consumption, so the consumption of the raw materials, they are always going to have those two dimensions, product and resource. Inventories are always on a product location. And then transfers, by transfers, I mean the intercompany movements like STRs, STOs. They will always have a product dimension from location and to location. And for the shipment, similarly, it's about the product, and then you ship it from an internal location to the customer. So you see how in all those supply chain concepts, we always use those 5 dimensions. So this is the data structure, those 5 dimensions, and all the concepts are built on them. And in particular, the variables and the constraints of the production planning solver. Now let's discuss about how can we best build a solver. And this is what we are going to follow in this course as well. So it's always good to have this phased approach, because as we know in optimization, sometimes when you add too many constraints at the same time, the results are a bit difficult to explain. So the explainability becomes a challenge. So it's best to add like one constraint at a time. Build one, check what's happening. Build the second one, check what's happening. So this is the idea with the phase approach. So here in the first phase, we are going to have this core of balancing demand and supply, such that we respect the capacity and the storage constraints. And then, so here we are going to talk about demand, about production, about capacity. And in phase 2, we are going to add target stocks, shelf life, and lot size constraints. These are not always necessary. Some companies don't have target stock, some don't have shelf life, some don't have lot size constraint. So that's why they're here in phase 2, because they are not needed to balance the demand and supply in all the companies. And eventually we'll talk about campaign planning, which is again a requirement that doesn't exist always. It's quite popular. And as I explained before, this is typically implemented using a mixed integer programming model, but we are going to see what are the various ways of going around that because MIPS are not very performant. And now here I wrote an example of a production planning solver in terms of inputs, outputs, and an example of objective, right? But in general, in supply chain, what we want to do, we want to minimize unmet demand. So we are going to talk in another lesson about unit optimization versus cost optimization. So in the solver that we are building now, we are going to have the unit optimization. So it means that in the objective function, we use penalties. So we want to have a penalty for the unmet demand, and we want the solver to minimize it. Then an example of another term in the objective function is that you don't want to go too much below target. So then you want to minimize that. And in the context of campaign planning, we want to minimize transitions. So we want to minimize the changeovers between the groups of products which go on a resource. And here are the typical inputs. So as I said, you can use this slide as a guideline for creating a design document. Because in a design document, what do you need to do? You need to include your objectives. So what is the objective of the solver? So this comes from the value proposition of the project, from what does success look like, and this kind of conversation. And then the input, it's data and constraints. But of course, also the constraints are type of data. They enter the solver as data. And here we start with the demand. So demand is always the driver of the solver because, as we said, we need to match demand with supply. So the input is demand, and it drives what happens in the solver. Then what is your initial inventory? So what is the product available in the first bucket of the horizon? The penalties, as I said, these are used in the unit optimization. For example, what is the penalty for unmet demand? And as an example, we say, well, I want to have 100 penalty for the unmet demand and 5 penalty for below target. So the penalty for unmet demand is very high compared to the below target. And then the solver becomes, you need to become a bit skilled in fine-tuning those penalties, like having the right ratios. Like, why did I say 100 here and 5 here? Well, this is what you start with. Then you look at the results, and after that you say, well, maybe the results are not good. So maybe change here 1,000,000 and here 1, okay? Because those penalties in the objective function are going to change the results of the solver. And finally, we have this kind of master data, BOM, rates, and calendar, which, yeah, they are basically the core of the solver. You match the supply based on mainly the rates, right? Because it's important, the speed at which you can produce. And of course, the BOM, the components, and the calendar, what is available. Sometimes you have holidays, you have setup times, you have maintenance, and so on. So this gives you, yeah, this is like the manufacturing particularities. And in terms of constraints, we have resource capacity. So what is your availability? You basically have a total capacity, and then using the calendar, you subtract. So then you have the available capacity. And this is going to be, it's as a constraint because the solver should not go above it, right? Then lot size, it's also quite fixed. So the solver needs to produce, let's say the lot size is 100. It either produces 100 or 101, 2, 3, or nothing. So this appears as a constraint. And also the target stock. The target stocks are usually soft constraints. So we are going to learn how to model hard constraints like resource capacity and soft constraints like target stocks. And then you run the solver, and then what do we get back? We get back the results which tell us which demand is met, which demand is unmet. Also the inventory projection, so the ending inventory for each bucket. And this is where the planner starts analyzing the plan. Then the production plan, what has been produced, where, and so on. Resource utilization, so how much of the available capacity is used to produce what we need. Storage capacity, and if we have campaign planning, you also have a campaign plan. Okay, so these are the typical inputs and outputs. When we have this for production planning, when we have network optimization, it changes, but not so much, because there we also have those deliveries to the customer. So we are going to have a report about the customer here. And now let's start about talking about the modeling. So this is a bit of a repeat information. As I said, in supply chain, we always have the same dimensions: product, location, resource, supplier, and of course we have the bucket, the period. So when we define the variables, we need to add product, location, and the period. So this is the power of optimization, that you can do this optimization over a full horizon. And that's not easy to do in Excel, for example. Starting inventory, ending inventory, as I said, they always have, they are on the product location and the bucket. Production, it's typically in product resource, but the resource belongs to location. And the period, transfers from location to location, product and period. And purchases, what I mentioned, sometimes you need to bring material from outside the company. So you'll always have the product, the supplier, the two locations, so where does it go, and the period. So these are the typical variables, or let's say the core variables. And of course, for example, when you have network optimization, you will also have the shipments, and the shipments will be from location to customer and period. But these are again, the core. This is the core structure which determine the core variables. And yeah, let's say the dimensions. And here just a few words about the objective function, which I already explained. And in this course, we are going to talk about the unit optimization. So if my objective function is about, I want to minimize unmet demand, and for example, ending inventory, then the skill is that you need to fine-tune those penalties. So how much penalty should I pay for not meeting the demand? In this case, I put 10, and ending inventory. In this case, I put 5. And for example, you'll see the first time we build a solver, we need to put a penalty for the ending inventory, because if you don't put, the solver will just produce infinitely, because it says, well, I do meet all my demand and I can produce as much as I want. So then at the beginning, when our objective function has only this term, the unmet demand, we also need to add a penalty for the ending inventory. And then we see that the solver just meets the demand, and that's it. So it produces only for the demand. And what I want to say is that the objective function also has a dimensionality. And depending of how you define here, the results will change. So for example, the granularity of the objective function can be product, location, period, but you can also have product and period. So the location is out. So this means that the penalty applies just for the product in all the locations. So the calculation is a little bit different. Or you can do only location, or you can remove the period and say just product location, and then it will take the full horizon. So there are two ways in which you can play with the objective function. One is the penalties, and one is the dimensionality of the constraint. And now I have some general remarks about solvers. So what is powerful about optimization is that everything is done at once. And what does this mean? All demands, all the supply, all the capacity are considered in one go. So the solver looks at everything and gives the optimal plan. And on the top of that, as I said, it looks at the full horizon. So for example, this results in a stock pre-built, right? Because for example, it looks at week 10 and it says, well, I actually don't have capacity to meet demand in week 10. So then it has a little bit of capacity in week 2. So they say, well, I'm going to use this capacity in week 2 to pre-build stock such that I met my demand in week 10. This is very powerful. The penalties and costs are accumulated over the full horizon. So again, it tries to minimize the penalty, the cost everywhere, not bucket by bucket, but in the full horizon, right? So it's a sum. And as I mentioned already, constraints can be soft, for example, targets, or hard, capacity. But we will see in this course, also capacity can be a soft constraint. And for example, when you have an MPS, so this is like a more operational plan, then the capacity is hard. So meaning I'm not allowed to go over 100%. The solver needs to find a solution such as capacity is at max 100%. Whereas if you model an RCCP, well, there is a bit more flexible, and you say, well, try to keep it within 100%, and if you go above, you pay a penalty. So this is the difference, and it's the same with the targets. Say, well, this is the target. If you go above, you pay a penalty. If you go below, you also pay a penalty. So yeah, those are two types of constraints. So I think this is what I wanted to tell you today. Now Felipe is going to switch to the app to show you the syntax, but we also wanted to mention a few resources that could help you with building the AMPL models. So first, the language. This is the first book. And then you have some examples. And what I like about this example is that you have the model files and the data. So you already can start modeling very quick because you don't need to search for some data files. And you also have the model that you can check if what you wrote is correctly. Then Python from plus AMPL, a collab collection of examples. And if you want to use AMPL combined with the Streamlit, which is a dashboarding tool, here you have the link. Okay, thanks a lot. And Felipe, you want to continue?
Yeah, let me share my screen. So in here, I'm going to show the app. The app is in fact built in Streamlit.
Right.
And I'm going to use the app to show an example introducing the syntax and going exactly over the same problem that Christine has just presented. So we have the products, we have locations. So in AMPL for this, we use sets. Then sets can also be combined sets. For instance, products locations. So in here we have a set products locations that is going to have just the valid pairs. This is a restrict table because a demand is indexed over. Demand is a parameter indexed over products, locations, and periods, but not necessarily for every pair. So we can have a set of valid pairs and then use it this way. So demand is then over the valid pairs of product locations and periods.
So the idea with those restrict table, I think we're going to talk about them in the course a bit more, is that you eliminate all the combinations which are not needed. And this increases a lot the performance of the solver. So that's the point of doing it.
Yeah, because this is something that often people forget, especially when they start modeling with a small amount of data. And then you end up with a model that you might not have just 3, but you might have like 5 or 6 sets. And then it easily explodes in size. And then it deteriorates the performance quite a bit when, in fact, when you just use a restrict table, you end up with a minimal model that is going to perform a lot better. So when declaring a parameter, you can also have some conditions on them for validating data, but other than that, the main purpose is to hold data. Then there are the variables, what we are going to be looking for when optimizing, also indexed over various sets. And once we have sets, parameters, and variables, we can define constraints. For instance, here, demand balance, which is also indexed. And then the condition that needs to be satisfied for every index of the constraint. The constraints can be simple like this, or can be more elaborated. For in this case, we have a constraint that in the first item is slightly different. In the first time period is slightly different from the remaining time periods. For instance, inventory carryover. If we are in the first period is just initial inventory. Otherwise is the inventory from the ending inventory from the previous period. And finally, after we have variables and constraints, we can also define objectives. Here we have that objective with the penalties. So we can use scalar parameters to configure these different penalties. So unmet demand, ending inventory. And then here we have the objective expression. In this case, we are summing our products, locations, and periods. And met demand times the amount of unmet demand plus ending inventory penalty times the ending inventory. And that's it. So once you know these concepts, you are ready to write models. The AMPL book is a good book to use as a reference for syntax. It's not something that you need to read end to end, but it's good in case you want to see exactly all the possibilities that are in terms of definitions of sets and parameters, and also variables and constraints. You can use it as a reference.
Yeah, and also in the book there are a lot of type of problems, right? So it's not just about the AMPL syntax, but for example, the diet problem, or then let's say production planning. I don't know, other problems they are described there. So you also get the modeling, the thinking.
Yeah. So the book, in fact, if you are really starting with optimization from scratch and really also want to learn optimization, that is also another purpose to go for the book, because it is going to also introduce that.
Can you go a bit up? Oh, sorry, I wanted to make a comment.
Yeah.
If you go to the demand, yeah, you see, so here in the demand paragraph, the demand is a parameter, but unmet demand and met demand, they are variables, right? Because the demand is an input, and then the other ones are variables. So they are in the same paragraph, but they have like kind of different, let's say, nature.
Yes. Yeah, because this is kind of is an input, and these are outputs, essentially what the solver is going to be optimizing.
Yeah. Okay, cool. Thanks. So let me share back my screen just to tell you what is the agenda for the next lesson. So we are going to start building. You already saw a little bit already. Also, Felipe showed you how the constraints look like. So we are going to build the demand constraint and also check the report. So that's the first report that helps us know if what we are doing is correct. Then we are going to add the inventory constraints and the material for constraints. And this is the equation of the core of the solver, what I explained in the first two lessons. It's the equation which basically says that demand equals supply. And we are going to add a few terms, because as the model grows, the terms increase, of course. And we are going to learn how to debug an infeasibility, because this is something that is difficult, and you need a little bit of experience and skill. So even with this small model, we are going to generate an infeasibility, and then we are going to see how can you find the issue. So the source of infeasibility has two main reasons. So the data or the modeling. Once the model is live, the infeasibility due to modeling are almost zero, but you'll keep getting infeasibility caused by data. So then this is a good skill to have. because the data constantly changes and can cause issues. So that's what we want to teach you next time. So thanks a lot for joining us. If you have any questions or comments, let us know, and we'll see you next time. Thank you.
Thank you.